completely fail. All right? And we as an engineer has to really be careful and raise a red flag. Any device you see that has potential adverse pressure gradient is on alert. Okay? And last time at the very end, I hastily discussed the difference between a turbulent boundary layer and a laminar boundary layer. And the characteristic of the laminar boundary layer is more energetic. Simply for the fact that it's fluctuating and there's a lot of random small scale motion that promote the mixing. That's what makes the dye in that pipe that we look at in the pipe flow completely burst, because all the molecule inside that pipe, once it's turbulent, is doing handshaking, doing wind dancing, going up and down, and completely chaotic. Because of that small energy, a turbulent boundary layer, just simply because of that small subtlety, has a little bit more momentum, just a touch more, so that I can negotiate or fight against that pressure gradient, even though it's an adverse. And as such, if the boundary layer is turbulent versus laminar, separation can be delayed, maybe by a fraction of the percent of the chord of the airfoil, 5% or even 10%. And that subtlety, that small differences, play a lot of first-order effect on many engineering devices. The simplest of which is the golf ball having dimples, which we will dive into now in detail. But this characteristic of making a boundary layer promote it or trip it or fool it to become turbulent is a characteristic we can deploy to our advantage, so that the boundary layer is a little bit more energetic and can fight against that pressure gradient just a little bit more. And for some aircraft engine application, that's huge. I told you the example of engine that fly very well with very good specific fuel consumption or fuel economy at low sea level, like 30,000 feet. But all of a sudden the military say, I want you to go to 60,000 feet because I want you to fly, no one can see you. That change in Reynolds number, that changed the transition location on those airfoil inside the engine, causes huge differences in the fuel consumption. And those are not simple tasks. So if you can somehow fool the boundary layer inside that engine at some location in the turbine and make them think they are turbulent and just be able to delay separation, that's gold. That's gold. And that's people will pay you a lot of money to hire you as an engineer to make that happen. All right? So, but we're going to focus on how this may manifest itself in a simple example of the golf ball. But that is just a very simple application. Okay? Any question on this concept of boundary layer? The fact that turbulent is what we want. And not to say in heat transfer, when you study that later on in your curriculum, that also has a huge impact. Turbulent boundary layer, because all the mixing enhanced heat transfer. So in a turbulent blade in an engine, there's a 3,000 degree Fahrenheit in the free stream. A turbulent boundary layer will absorb more heat onto the blade and can, if you're not careful, melt the blade. Whereas the laminar boundary layer, the heat transfer is a little less. So all those are heat transfer engineering that people try to understand the boundary layer behavior and use that to study heat transfer. Okay? Questions? All right, so golf ball, dimples, why? So we're going to look at an experiment of which we measure the drag on a sphere. When did we study that? Anyone can remind me? Have we studied that problem before? How about in dimensional analysis? Chapter 7. What have we concluded based on dimensional analysis? Anyone quick? What are the important parameters that would dictate the drag of a sphere? This is just a recap. Drag force as a function of anyone? Diameter, yeah, diameter, size. What else? Fluid, viscosity, and what else? Density, very good. Anything? Anything? Velocity, and that's it. And from dimensional analysis, just like you did for test 2, you don't have to think. What this dimensional analysis will tell you is, how many pi terms? 2, 3, 4, 2, right? N minus 3. The first one on the left is the drag coefficient. Which is force divided by pressure, which is dynamic pressure, rho v squared, divided by an area which is problem dependent. For the sphere, we take the cross-sectional area, pi r squared, but there can be other area that is equally appropriate, and it's just depending on what you're looking for in terms of normalization. And in the table, in your text, the area will be defined for you. And the other pi term is simply the Reynolds number. So from chapter 7, we know to determine the drag on the sphere, all I have to tell you is only one number. What's that number? What's that number? Based on dimensional analysis, to tell you the drag coefficient, what that will give you. Just one thing. Reynolds number, not the fluid viscosity, not the fluid density, but normalized it, dimensionalized it, simplified it. One and only one thing, Reynolds number. Do you remember that? So with that, if I'm going to do an experiment, I'm going to do it in air, and then in water, and then in oil, because they're all redundant. I only need to do it once. And preferably in air. And I'll present the result to you in what form? What will be the x-axis? What will be the y-axis? If you were to do this experiment. We went through that in chapter 7, remember? We went through that for an airfoil, we went through that for pipe flow, we went through that for a sphere. All the same. What's the x-axis? Reynolds number. What's the y-axis? There's only two things. 1, 2. My hands are bound. You give me a Reynolds number, I have to give you one and only one thing. The drag coefficient. No ambiguity. They're unique. Give me a Reynolds number, I can only give you one number which corresponds to the drag for a given shape, which is a sphere. Not the size, not the fluid, but all are normalized. Do you understand that from chapter 7? This is something you may see again in the finals. Do I have to go back to this? Any question, please? Yes?
So is it that C is equal to drag number or the function?
No, it's a function of, not equal to. Very important. At this point, in chapter 7, I have no idea what function it looked like until I do an experiment. That, again, is like the pipe flow. I have no way of knowing how the friction factor behaves with the other perimeter until Mr. Moody do the experiment. Right? That's very important subtlety, but I try to emphasize that many times. Dimensional analysis only gets you to this point, but nothing more. The rest is experimentation. Other questions? So now we're going to do a deep dive into what that shape look like, which again, I repeat, can only be done by an experiment in the laboratory. So the shape of the graph with Reynolds number starting very small to a very interesting 5 million Reynolds number, and I'll illustrate that momentarily. where the drag coefficient on the log scale, log scale, ranges from small 0.01, and there are two values of particular interest of 0.2 and a half, and then all the way to, say, 100 of the dimensionless drag coefficient. So it's a log scale. What does that remind you of? What was plot you have seen so far that's also plotted log scale where the x-axis is also the Reynolds number? Moody, yes, Moody. There's some analogy in which you see momentarily. So instead of drag coefficient, the Moody diagram is in terms of this friction factor. And it turns out indeed, for Reynolds number that is very small on the far left of this diagram, 0.1, 0.2, 0.5, even 1. When the Reynolds number is very, very small. When I say that, immediately what you can tell me regarding the concept of a boundary layer. Remember what I emphasized. Remember your homework. Remember that small minnow swimming in water. Remember that small fly flying around in the room. What does that imply? There's no boundary layer. The boundary layer concept completely breaks down because there's no small layer anymore. Viscous effect is as dominant as the inertial effect. So the key takeaway for small Reynolds number, and I want you to remember that, and I may quiz you on future lecture or in the final is, hey, when there's small Reynolds number, how small is small? 100, even 1,000? Boundary layer doesn't exist. You can't use that concept anymore. So no boundary layer, and for that actually, because there's no boundary layer, the concept of full separation is not even conceivable, because when there's no boundary, there's no separation. The flow is separated everywhere. All right? An example of this type of flow, if you will visualize that, is if I have a column of very viscous fluid. Could be oil, could be gelatin, where I drop a marble, a sphere.